Thank you everyone for attending in such a nice day in Gothenburg. I arrived yesterday and it really has been it's a really nice city and hope to visit once again. So my name is Waldemar Quevedo, but most people call me Wally. I'm one of the core contributors to the NATS project. I have been using NATS-based systems for around 6 years already. I originally became familiar with the project through Cloud Foundry. So that's another question. How many of you have heard about Cloud Foundry? Several hands. And so yeah, I was part of the team that introduced Cloud Foundry into this big e-commerce website that was using, well, one of the main components there was NATS, right? So, and it has been a great being able to use NATS for distributed systems since then. So this is cloud native messaging with NATS. And our agenda is first going to give you a quick introduction about the NATS project. Then I'll make an overview of both NATS and NATS streaming, which are the two main server implementations from the project. And finally, give you some demos of how to use NATS and NATS streaming. So NATS is a simple, high-performance messaging, open source messaging system for cloud-native applications. And some facts about NATS: it was written by Derek Collison in 2010. Again, originally for Cloud Foundry. It was actually developed in Ruby using Event Machine, and as was most of the components from Cloud Foundry at that time. It was, even though it was still Ruby, it was already pretty fast. It could push around 150,000 messages per second, but it was rewritten into Go in 2012, and now it's way, way, way faster. It has been used in production environments for around 7 years, I think, now. And the last year, it reached the version 1 milestone in July 2017. And another milestone is that this year it joined CNCF as an incubation project in a couple of months ago. This also meant that we had to change the licenses from MIT license to the Apache 2 license. So that's a recent change from being part of the CNCF. And if I have to tell you one single thing about NATS, is that it is very fast. So NATS, to give you some stats, a single server can push around 11 million messages per second. This is, you can see from the benchmark tool that it can also get around even 14 million messages. These are very small messages, but it can give you an idea of how fast it is at signaling everyone that is connected with the lowest latency as possible. And well, this is using the NATS bench tool that you can find it under the NATS.io Go NATS repo. And another cool thing about NATS is that it gives you this very predictable low latency. So here is a comparison with NATS and RabbitMQ using a 1 kilobyte payload. You can see that, well, NATS is the line that is here at the bottom. You can see as the tail latencies increase, as you for RabbitMQ, while for NATS it's mostly flat and very predictable, the type of growth. So in case you have a system where you need to consider the SLAs of your project, then NATS is very, very reliable for that. Recently, Derek, who created NATS, tried the NATS benchmark once again with a fairly powerful machine, and you can see that with, in this case, 16 publishers with also small payload sizes, you can send like 72 million messages per second with a single server. The gist is at the bottom as well, and I can show you the slides later. Another cool trait from NATS is that it is very simple. So about the simplicity from NATS, one of the foundations from NATS is this very simple protocol. It is plain text protocol, similar decision as in Redis. And you can see from Redis that it's basically there's a client for almost every runtime from Redis, right? And that is thanks to having this approachable protocol that you can, well, start publishing messages right away. It is 10 commands. At its core, NATS is a pure publish subscribe engine. So you can publish, subscribe, you can unsubscribe from messages. And there's also some basic, well, ping and pong and error notifications from the server. And I think it's a fun protocol to implement if you are learning a new language. It is it is a fire and forget pure publish subscribe on top of TCP/IP, and it can be made secure by default with TLS. Here at the bottom is an example of doing a telnet basic session to demo.nats.io into the 4222 port. And here you're making a subscription to the Fika subject, so you can get notified when there is a time for Fika. And you're publishing to anyone that is has registered interest into this Fika subject that it is Fika time for Fika. And so anyone that has registered interest into this subject will receive the message. And something important to note is that the maximum payload size is by default 1 megabyte, right? So this can give you an idea of the type of systems that you will be building with using NATS, right? So in case you want to transport like several megabytes of data at once, then you will, if you really want to use NATS for that, you have to start chunking, right? So, but in case of anything lower than 1 megabyte, NATS really excels at publishing data with that. This is the default. You can tune the maximum payload size to, for example, 5 megabytes. And we have seen some deployments in production that have done that, and it works fairly well. We have several clients available, all supported officially by the NATS team. The main implementation is the Go client. The Go client is the one that has the latest features all the time. Here is an example of the basic API. You can connect to comma-separated list of the servers, the NATS servers. Then here you're making a subscription to the Fika subject that is going to, under the hood, become the protocol that I showed you in the slide, the previous slide. Then you set the publish command to send a message. And that is the simplest publish subscribe example from NATS. There is a similar API with the Ruby client for asynchronous subscribers. We have Python clients are using async.io, which is starting to get more popular, actually. Python 2 is going to be out of support, I think, a couple of years now. And Node.js is one of the most popular clients with a lot of dozens of downloads. The C client, it was in case for constrained environments, has its own adoption. There is a C# client. This one is also fairly popular. And of course, a Java client. We have all of these, again, supported by the NATS team officially, right? So that we keep them up to date with the protocol. So about what are the messaging techniques you can do with NATS? There are three main types of communication you can do. One is the basic is basic publish subscribe, so you can communicate one-to-one, send a message to one-to-one subscribers. A variation from this, you cannot see this, maybe you can see, okay. You can use distribution queues so that each time that you publish a message, only one of the subscribers is going to receive the message randomly. So it is not round robin, it's randomly one of them is going to receive the message. And the third type of interaction you can have is the request response. And the request response, it is again using the lower publish subscribe protocol, but the way it works is that it uses unique ephemeral subjects for the messages. So each one of the messages that are published, they create this unique identifier. And then, by definition, the subscriber that is going to be replying to the message is the one that is the fastest. So now this is how NATS guarantees you to give you the lowest latency response all the time. Yeah, the lesson from this, according to that, it comes from the way that Google does things, where you can a lot of components that are failing all the time, And even though there could be many available to process a single request, then the only thing you care about is the fastest response, the fastest node that can help you process that message. And you can combine the request response from using the distribution queues, so you can send a request, and then only one of them is going to be processing the message. And so these are the three main features in terms of the protocol from NATS, and then everything builds on top of this. You can use wildcards as well for the subject's routings. There are two types of wildcards. One of them is the partial token wildcard, which is expressed with the asterisk. So in this case, you can use dots to separate the subject. In this case, foo.**bar. Then any message that is published into anything that matches to the asterisk in the middle is going to receive the message. And this can be very useful for when you want to have a periodic heartbeat, for example, and then discover that whoever is connecting to the system. Or in case you're using because we use this inbox prefix for all the requests that are happening. So you can also subscribe to the _inbox .star, and that way you can see all the requests that are happening through NATS without affecting the other subscribers that are processing the messages. So this can be a useful way to basically tap into anything that is happening and audit, for example, all the communication between the consumers. The other stronger variation from the wildcards is the full wildcard, which is expressed with a greater than. In this case, it will not only match in a single namespace from the subject, but instead will match everything from after that point, after that dot. So this one is fairly strong. So if you use it at the root level, so for example, subscribe into greater than everything, you see really everything, every single message that is being published through NATS. And again, all of this without affecting any of the other clients. So it is really good for auditing and doesn't affect the performance. There is also authorization on the subjects. So you can, for example, by default, you cannot publish a message under the /sys subject namespace. You will get a permission error. This is only internally used by the servers. And you can customize who is allowed to publish and subscribe into these several subjects. A pending item in the roadmap is to make it pluggable with different authentication providers. So right now, the workaround to be able to update these rules is by using the server reload feature. So you can send a hop signal to the server and then have a new set of authorization rules to update the newest policy. And the previous examples were using a single NATS server, but you can make this highly available by using the full mesh cluster topology. It is a full mesh, one hop type of setup. So it is important for all the NATS servers to know all the peers inside of the network. In case there is a disconnection between the servers, then there is not going to be routing happening between the clients, right? So this allows you to, as a client, to just connect to any node that is part of the cluster, and then the NATS server is going to be routing the messages according to the interest graph. And because of the internal reconnection logic that all the clients implement, in case the NATS server that you are connected to fails, then it will back off for 2 seconds and then try to reconnect as soon as possible to another available node. Something that's very useful for cloud-native environments is the cluster auto-discovery mechanism that is using the info protocol from NATS. So in this case, you can start with a single node. Let's say you're scaling up a NATS cluster in Kubernetes. And you can start with a single node, and then this one becomes the seed server. And then you scale it up to another node, and then it is going to be announced where is the next this new server that has joined the cluster. And all the clients are going to reconfigure and be aware of where is the new network endpoint from this, that joined the cluster. And again, if you add another node and it joins, it will be through the gossip via info, receive every client will be aware of where is the new server. So in case it fails, they will all reconnect to one of the other available nodes randomly, right? So, and the third main aspect I want to cover about NATS is that it is very resilient. So NATS, unlike other messaging systems where they try to bend over backwards to try to deliver a message, NATS really goes the complete opposite way. I mean, for NATS, the most important thing is to provide a dial tone for the clients to be able to communicate. So in case there is a client that is not performing very well, NATS will prioritize the service uptime instead of like doing extra work for that client. So we say that NATS protects itself at all costs. For example, this is, let's say you have a client that is publishing as many messages as possible onto this hello subject, and it has registered interest into this hello subscription. Because it has a tight loop that and making the asynchronous engine from the client send as many messages as possible, then the server will try to be delivering all of these messages that it is itself sending, and without being able to process them, right? So what is going to be happening here is that the server is going to be accumulating a lot of data for this client, which is not a healthy situation. So the server, what it will do is disconnect the client with this slow consumer error. Yeah, so this is basically how NATS processes things. In case basically there is a error, in case there is something failing in the cluster, and you just like disconnect everyone else, and I mean, you're out. So about delivery guarantees from NATS, NATS again is a fire and forget system, and it only gives you an at most once delivery, because if you're not connected by the time you were a slow consumer and lost the message, then NATS will not redeliver that message. Is everyone familiar with this book, or have you seen it? It's about. Oh, okay. So it's a really interesting book where NATS is covered a little bit here, and under the modes of data flow chapter. But it is so it is mentioned as one of different solutions as a message broker, which is interesting because it doesn't really map to the definition that is provided here. For example, it says that a message broker is also known as a message queue. It's essentially a kind of database that is optimized for handling message streams. And NATS doesn't really do that. And it also says that by centralizing the data in the broker, the systems can more easily tolerate clients that come and go, because the question of durability is moved to the broker instead. So again, NATS doesn't do any of that. Then the third one is that faced with slow consumers, they generally allow unbounded queuing. So as I mentioned in the previous slides, NATS will just disconnect you and discard those messages. So it's, when considering whether NATS is a message broker queue, NATS server itself, or what we would say is a core NATS, it's kind of like the complete opposite from this definition. But still, I mean, there was a lot of we listened to the users and the type of APIs that we're expecting from. We're fairly familiar with this, the way these messaging queue systems work already. So one thing with NATS is that you can always build stronger guarantees on top. So we have a new project, but no longer new, was released a couple of years ago, named Stan. Stan because it is the opposite from NATS. The name didn't stick, but so we renamed it into NATS Streaming. And NATS Streaming is kind of like the opposite from NATS. And so NATS Streaming is, unlike NATS, provides you with at least once delivery semantics. So it has persistence of messages, there is rate limiting using ACKs, and in case you disconnect, it will, you're able to replay all the messages from the beginning of a certain point in time. Again, it has been out there for 2 years. And it is built on top of the NATS protocol itself using the request response APIs. So it is using the request response and using protocol buffers as a serialization format, since NATS doesn't constrain you to any type of serialization format, right? So you can use message pack or JSON for communicating. And in the case of NATS streaming, which is essentially a NATS application, we decided to use protocol buffers. A production setup may look something like this. You can have a highly available NATS cluster where your clients will be connected, and then NATS streaming will be connected to one of them. And then for each one of the application runtimes, we also have a special NATS streaming library that is going to implement the request response protocol. And then through NATS, the clients connect to the NATS streaming server. And because it is using the NATS as a lower layer, then if one of the NATS nodes fails, then it will transparently reconnect to one of the remaining NATS nodes. Since there is persistence, then for NATS streaming server, besides the high availability of the transport from NATS, we also need to talk about the high availability of the persistence messages as well. So in this case, we have a raft implemented for the NATS streaming. So it uses the NATS as a transport for doing the replication of the logs that are published and subscribed and consumed by the clients. So as it tends to be with NATS, with raft-based setups, it is recommended to have like 3 nodes at least to join the quorum, or not fairly large raft groups in case. But because we are using the same NATS transport, we can separate, for example, on a different name, the multiple NATS clusters, NATS streaming clusters. And the API for NATS streaming is fairly similar to the NATS API. Here is an example of publishing a message, just publishing foo on the hello world message on foo. And also similar asynchronous subscribers that you can receive all the messages by using this stand deliver all available messages. So internally what will happen is that it's going to make a request to the NATS streaming server to replay all the messages that have been published since the beginning from this subscription. You also have available clients for multiple runtimes. There is one for Ruby. And as you can see, here the name stan really stick because it is shorter. So you would see in NATS streaming code import NATS or require stan. And you can mix the NATS connection to then mount the NATS streaming connection on this the NATS connection. So here's an example of the Python client, the async IO client. There's one for Node.js as well, and of course Java support, C#. So quick recap of the current state then is there is a NATS server. The binary name is gnatsd. That one provides you with advanced once delivery guarantees. So there is no persistence of messages. You have to be connected in order to consume the message. And there is also the NATS streaming server, which we used to call stan. But you can also still see the name stan in the client libraries. This one, the binary name is NATS streaming server, and this one provides you with at least once delivery semantics, so you can replay the messages. And NATS streaming itself, it's built by using NATS as a transport. Any questions at this point? Or? Okay, so. Then it's, I don't know, maybe like if this was popular here, maybe it will not work. So this is NATS and NATS streaming, as explained by 2 Angry Men. The reason we use, there is a, actually you can get by a lot with just like pure NATS. So you can say that you don't really need persistence of messages many times, right? Because you can just like idempotency, semantics to be able to get by. But then we did end up implementing a NATS streaming for at least once delivery, right? So there's like a need for that. But we were very wary of the end-to-end argument in this case, where the end-to-end argument where it says is that you have to be careful of adding too much into the lower layers because that can constrain you in the end. So that's why we decided to just implement NATS streaming as a layer on top of NATS, because that way you're really not constrained into this how to say it. But it doesn't constrain implementation because you can still opt to just use NATS for publish subscribe. And so that's it for the talk. And also a quick announcement is that there is I have just finished the first book on NATS. It will be coming out in July. So yeah, definitely check it out once it's out. And so any questions? That's a good question, but in the documentation we say that we only talk about it after a beer.